So in the previous video, we looked at a few different concentration units, and we discussed some new ones that we haven't necessarily used that much or utilized that much in class or in lab, which is molality and mole fraction. And we're going to talk about why we actually care about or need to use those units because we're going to focus on this idea of colligative properties. Okay, so colligative properties are simply physical properties of a solution that change based upon the number of particles dissolved, not necessarily what's dissolved. So if you dissolve 17 particles of a molecular compound versus 17 ions dissolved in a solution, it doesn't matter. Okay, it doesn't matter what's dissolved, it just matters the total number of particles that are dissolved into that solution. Okay, and so we're going to see there's four different colligative properties, or four different physical properties that are related to the amount of solute dissolved in a solution. Okay, so these four properties are described by various different relationships or laws. Okay, the first one is Raoult's law. Okay, so Raoult's law deals with this idea of vapor pressure and what happens to the vapor pressure when we add a non-volatile solute. Okay, so Raoult's law describes the vapor pressure depression or decrease by the addition of a non-volatile solute. Okay, so a non-volatile solute just means something that we dissolve maybe into water or cyclohexane or some solvent that doesn't actually contribute to the vapor pressure because it's not something that's volatile. It doesn't actually evaporate off and create a vapor pressure above the liquid. Okay, that would create a lot of different other issues if we dealt with something that were volatile solutes. Okay, so we have the addition of a non-volatile solute, and that causes the vapor pressure to decrease. Okay, we can describe this by the pressure of our solution. Okay, so the vapor pressure that our solution exerts, that's equal to the mole fraction of the solvent times the vapor pressure of that pure solvent. Okay, so this is the vapor pressure of our solution. This would be the mole fraction of our solvent. So that would be the number of moles of our solvent divided by the total number of moles. Okay, and then this is the vapor pressure of our pure solvent. So we haven't added anything into it. That's just what the vapor pressure would be. Okay, and so we see that we have this relationship. As long as we know what the vapor pressure of our pure solvent is and how much of our solute we added, we can actually determine our mole fraction, and then that would tell us our vapor pressure of our solution. So we'll notice as we add more and more and more and more solute, the mole fraction of our solvent decreases, right? Because our total number of moles would increase. It wouldn't really affect our solvent. And so that would affect this mole fraction and cause it to decrease. Okay. So what we'll notice is as we increase the concentration of the solute, what we'll notice is that our vapor pressure is going to decrease. Okay, and remember, this is at a specific temperature. Our vapor pressure is dependent on temperature as well. So we're looking at a specific temperature. So this is one of our physical properties that is affected by how much is dissolved into it. Okay. Our second, and I'm going to kind of group these two together, is dealing with our freezing point depression and our boiling point elevation. Okay, so as you dissolve more and more solute, we're going to notice that our freezing point goes down and our boiling point goes up. Okay, and we can describe these mathematically by saying that the change in our freezing point is equal to a proportionality factor. Okay, it's called our freezing point depression constant times the molality. Okay, and then we could also say for our boiling point as a similar relationship where it's the change in our boiling point temperature from normal equals the boiling point elevation constant times the molality of the solution. Okay, so again, in the last video, we talked about calculating molality. Okay, now the reason why we use molality or why we use mole fraction is that we'll notice that these concentration units are not temperature dependent. They won't change. So if we decrease our temperature, increase our temperature of the solution, these are not going to change in their units. Whereas something like molarity, percent by volume, anything that has a volume relationship in that concentration unit is going to be affected by temperature. Because as you increase the temperature, our volume of our solution is going to increase slightly, which affects our concentration without us actually adding more solute or adding more solvent. Okay, so we use molarity, and we use mole fraction because both of those are temperature independent. They will not change if you change the temperature. Okay, and so we can use each of these. You notice that we have two different constants. Okay, those are different values. We're not going to, the freezing point depression constant is not the same as the boiling point elevation constant for water or for cyclohexane or something. Another thing to note for each of these, okay, that is dependent on what the solvent is. Okay, it doesn't matter what the solute particles are, right? Which goes back to the original idea of a colligative property is it only depends on how much is dissolved, not necessarily what is dissolved. So the freezing point depression, the boiling point elevation, those are related to the solvent, which typically is going to be water, right? And so we can look those up. Those are tabulated values. And so we see as we increase the concentration, the amount that our freezing point decreases or the amount that our boiling point elevates gets larger and larger and larger as we have higher and higher concentrations. Okay. So as a note, this is kind of why the reasons if you live somewhere where there's lots of ice or there's lots of snow, they add salt to the roads because you're increasing the concentration of those salt particles, the ions, and that causes the freezing point to decrease, which makes things melt at a lower temperature, and so therefore you have water sitting on the road instead of ice or snow, which is going to be safer to drive on, right? So that's why you would actually add things to our, in that case, ice or snow to cause it to melt at a lower temperature, and therefore you have a lower freezing point, okay? The fourth one is osmotic pressure, okay? So now osmotic pressure is a pressure that is created when we have a solution and we have like a pure solvent. Well, the pure solvent's going to want to move into the solution, okay? We don't necessarily have time to discuss this in this video, okay? But what we'll notice is that our osmotic pressure, which is pi, equals the molarity of our solution times R times T, okay? And so this is the molarity. This would be our temperature in Kelvin, and that's our normal gas constant, 0.0821 liters atmospheres per mole Kelvin. Okay, so now we can use molarity for osmotic pressure because we're measuring at a specific temperature. It's not looking at how these physical properties affect the temperatures. Okay, and so we'll notice that we can use molarity if we're dealing with osmotic pressure because we're not looking at temperature changes with our osmotic pressure. Okay. So this gives I just wanted to give us an overview of these colligative properties and really emphasize, okay, it's dependent on the number of particles, not, okay, on what's actually dissolved. If I have 2 moles of ions, or if I have 2 moles of a molecular compound like sugar, it doesn't matter. It's going to have the same effect on the freezing point depression, boiling point elevation, dealing with our vapor pressure decreasing, and then osmotic pressure. Okay, so hopefully this gives us a good introduction to this. In class, we're going to really look at how do we actually determine how much our vapor pressure decreases, or our freezing point decreases, or our boiling point gets elevated when we look at the specifics of each of these.